Okay, this is the first part of section 8.3, estimating a population mean using a confidence interval. All right, so if you look, trying to explain here the new t distribution. Sampling distribution of x bar is sometimes normally distributed. We know if the population's normal, the sampling distribution of x bar will be normal. If we know our sample size is big enough, is 30 or more, then we know it will be approximately normal. So here is how we standardize. Z is equal to the x bar minus mu over the standard deviation of the sampling distribution. The issue that we have is that we're assuming we know sigma, but in reality, we won't know sigma. So here we have a sampling distribution of the x bar. We will standardize that. So find the z score for where we are on the distribution by using the formula for z. The key here is that the sampling distribution of x bar has a sigma in it, and we don't really know what sigma is because we don't know what the parameters are. So in reality, we will be substituting our sample, the data sample will have a standard deviation. We refer to that as S rather than sigma because it's not from a population but from a sample. So the standard deviation of the sample S will be substituted in for sigma. The problem is that this distribution, unlike the one up here where we have Z, we don't know what this one is. Well, we will know in a minute, but as of right now, that is not going to result in a standardized normal curve. It's going to result in a different type of curve. So if we look at this slide, we have a computer simulation of a bunch of confidence intervals. So we're trying to estimate mean, and what we're going to assume is when we go to standardize, let's assume for the time being that we're standardizing going into a z-score, assuming that we have a normal distribution of the sampling distribution. When we standardize, we are going to turn it into a z. Now, we know that we don't have sigma, so we're in our conversion, we're going to be using S rather than our sigma. So what happens? All right, so let's look at what happened here. We have a confidence interval of 95%. We sampled 100, we created 100 samples. We would expect to capture the mean in those confidence intervals from those 100 samples 95 times, but we got 87 capture rate. So we only captured the mean 87% of the time if we look at these 100 confidence intervals. So something's going on, and the issue is that when we standardize, when we use a z together with we assume it's a normal distribution, but when we use s in our calculation, the calculation is off, and that's what causes, even though we're using a confidence interval of 95% confidence level, that's why we're only getting 87% confidence capture rate. And so something's going on, and we have to figure this out. So the normal curve is not appropriate. So if we look at a demonstration of the normal curve, the one on the bottom is a normal curve, and the one on the top is a t distribution. You can see the t distribution is a little bit wider, and so if we assume we have a normal distribution when we don't really, that's going to mean that the confidence intervals that we are creating are going to be a little bit narrower and not capture the true mean as often as we would like. And so that's why in the last slide we got a capture rate lower than we should have. All right, so a t distribution is what we end up having. The whole point is that we have this t distribution because we used our sample data in the form of a standard deviation of the sample rather than the standard deviation of the population, which is just not known. Okay. So what's the properties of the t distribution? So we we call this a t-distribution, first and foremost. It's called a t-distribution. It has a shape that's similar to but different from the standard normal curve. We almost think of the t-distribution as a standardized curve, but it's not a standard normal curve. It is symmetric and has a single peak at 0, just like our normal curve. However, you can see much more area under that curve. I mean, these are not curves that we see on this slide, but these are computer simulations. But you can see if we drew, a curve over this, okay, that's a horrible curve. But if we drew a curve over it, we would see that there's a lot more area in the tails than in a normal curve. All right. All right, so what makes it even more complicated is the t-distribution changes with the sample size. So the normal curve, standardized normal curve, does not change with sample size, but the t-distribution curve does change with sample size, and we refer to it as the degrees of freedom. Degrees of freedom are simply one less than the sample size. So if I had a sample size of 30, my degrees of freedom would be 29. All right, so here is the formula for the t-value. So just like we would have a z-score, we have a t-score. So with this t-score, we also have to concern ourselves with what we abbreviate as df, the degrees of freedom. So with the t-value and the degrees of freedom, we can do calculations, and we'll see more kind of how to do this as we proceed through this chapter. Okay, so this slide simply shows you the similarities and differences between the normal curve and a number of t-distributions of various degrees of freedom. So we see the purple graph is the normal curve. The other two graphs are t-distributions. Notice the main difference is that the t-distributions have less area under the curve in the middle and more area out in the tails. Here we show how to find the critical t-values needed for calculating your confidence interval. We want a 95% confidence interval with a sample size of 12. That means our degrees of freedoms will be 11. If we look at the row number 11 on the T table, sometimes referred to as table B because it's the second table in our book, you would then also look at the column for 95%, and where those two columns, the row and the column intersect, give us our critical value. We can also find that using our calculators with an area, of course, of 0.025 and a degrees freedom of 11. They give comparable values. Okay, this slide talks about the limitations of our critical finding our critical t value from our limitations on our t table. If we're looking for a 90% confidence interval and we have a sample size of 48, the critical t value will be found by first calculating our degrees of freedom of 47. However, when we go look at the table, you'll see a 47 is not on the degrees of freedom. So we will always go down in value to 40. So we look at the 40 together with the column of 90%, and that gives us a critical t value of 1.684. Just know that when you do use your calculator, you can actually put the 47 in your calculator. It's just the limit. It's not the 47's not there. It's just that 47 is just not listed on our table. So in that case, we always go down when we're using our table. But if you're using your calculator, you actually put the 47 in, no problem. All right, the conditions that we need to check for confidence intervals for means. So the first two are the same as we did for the confidence intervals for proportions. Randomization has to be from a random sample or a randomized experiment. We'll talk about randomized experiments more in future chapters. For now, we do mostly random sampling. 10% cannot sample more than 10% of the population, assuming, of course, that we are not replacing, which in most cases we don't. All right, the three other cases we have to consider for the normality of the sampling distribution. So yes, we will have on some cases a normal sampling distribution for X bar. just realize that yes, we're using a t-distribution, but that's because we are standardizing. And when we standardize to a normal curve, the curve is actually not normal anymore. But the sampling distribution will still be normal in some cases. Okay, so the three cases, some of these we've seen before. First one, if the population is known to be a normal distribution, then we know our sampling distribution will be normal, and we can proceed with our t procedures in that case. Number two, the population distribution is either unknown or is known not to be normal, but our sample size is large enough, 30 or more. This will give us the ability, using the central limit theorem, to proceed with our t procedures. The third case is neither of those things happen. Population distribution is unknown or is known to be non-normal, and our sample size is lower than 30. Then what we do is we simply graph our sample data and look to see if there are any outliers. Is there really strong skewness? Now, just because you select a small sample from a population that is perfectly normal, you may still not get your sample data to look very normal, even if it does come from a population. So we are going to look for really strong outliers. Look at an example. So if I took my calculator and I had it generate 20 data values at random from a normal distribution with a mean of 100 and a standard deviation of 15, and then I store it in list 1. And now I can take that list 1 and I can ask the calculator to plot it. I can either plot it with a histogram or plot it with a dot plot, a box plot. Let's see what happens when we do that. So if I took that data, everyone's data would be different because every calculator is going to create 20 different random. But you can see here, even though I've taken data from a perfectly normal population, because that's what I've asked the calculator to do, the histogram still kind of looks a little bit skewed. So we're not going to be looking for perfect symmetry. A little skewness is okay. We just don't want strong skewness, or worst case, outliers. And outliers are really easy to check for when you do a box plot. So my box plot, I use modified box plot, does not show any outliers, and it appears fairly symmetrical. Okay, and then of course the third option for graphing it would be to look at a normal probability plot. Remember, for normal probability plots, we are looking for straight lines in the data. If the data is fairly straight in the normal probability plot, we can assume it's fairly normal. So basically what it boils down to is if the data, when we plot it, our sample data, looks not to be too skewed or not to have any outliers, if it looks kind of normal-ish, then we're going to assume that we can proceed with our t procedures. Okay, so basically look for outliers. If there's no outliers, we can pretty much assume we're safe to go. All right, here are 3 examples that we want to investigate as to whether or not we can proceed. This is, checking the third condition, the normality of our sampling distribution. So we don't know in any of these cases whether or not the population is normal. So we'll have to investigate the shape of the data in some cases to see whether or not we can proceed. So the first one wants to estimate the time in a coffee shop. We have 5 pieces of data, too few data to be able to say for sure that our sampling distribution is normal. We have an outlier, so in that case, we're going to say no, the sample's too small, so there's an obvious outlier. We will not be able to calculate our confidence interval. The next one does appear, this is the average height of high school students. We looked at 100 randomly selected students. There are 2 outliers. However, that doesn't really matter because we sampled more than 30 students. And so yes, even though there does appear to be outliers in our data, it still looks pretty symmetrical. The central limit theorem tells us that we can proceed with calculating our confidence interval, the sampling distribution of X bar. It will be approximately normal. All right, part C, middle school counselors want to estimate the number of minutes students spent doing homework. We have 20 students. The sample is too small for a central limit theorem to tell us that the sampling distribution of X bar is approximately normal. So we look at the sample data. It's plotted down below here in a histogram. Does not appear to have any outliers. Does not appear to have any strong skewness. So we will proceed. Yes, there is no strong skewness or outliers. We will proceed with our calculation of our confidence interval. We'll look at how to actually calculate those in the next half of this data, of the slides.